Thanks everyone for joining this morning or evening. So I'm Kashif Nawaz. I am the group leader for the multifunctional equipment integration at Oak Ridge National Lab, and have been serving as a liaison for the CHP program here at Oak Ridge. So this is some high-level points which I'll be briefly going through, and I'll be talking about some of the enabling technologies. I guess the previous speakers, they gave a very good background about why the heat pumps are important and where we stand. I'll be highlighting some of the major issues and hopefully posing some right questions which can ignite some follow-up discussion. We're talking about integration opportunities in buildings. Certainly, there has been a lot of paper studies, or I should say academic analysis, but when it comes to the actual deployment, there are obviously challenges. And then in the end, I'll highlight some thoughts about the research priorities when it comes to the low temperature systems. So the very first thing which comes to mind when we talk about the high temperature heat pumps, or in general, any waste heat recovery process, I think heat exchangers are essentially one of the key components which must be considered when it comes to the design of the overall system. So there has been obviously a lot of efforts in design of microchannel and braze plate heat exchangers, which are much more compact and efficient compared to the conventional technologies. However, when we start looking at I'll call it intermediate temperature range because that's a relative term. That is an area where there is still a lot of potential and further developments are required. When we consider the heat exchanger design, it has to be really based on the specific application, and we have to consider all aspects, including such as design, material, and manufacturing process, in order to get some cost-effective and efficient solution. Low pressure, well, there are obviously systems which can operate at low pressure. The conventional heat pumps for water heating, air heating, they have been using round tube fin heat exchangers. But when it comes to, say, systems such as supercritical CO2, there has been a lot of interest, as has been highlighted by the previous speakers. They actually pose some special challenge because you obviously need the right infrastructure. And of course, heat pipes and the vapor chambers, those are some passive heat exchangers. I call them passive, they're also important. At the bottom, you can see some of the work which we have been doing here at Oak Ridge on the gas-to-gas heat exchangers, and they are some of the, I'll say, latest development on the ceramic-based devices, much more efficient compared to the metals and metal-based solution, but they're also quite cost-effective compared to the existing solutions. So moving on, as I noted earlier, there are obviously several opportunities to explore non-metallic solutions when it comes to the heat exchanger devices, because there is actually a general misconception that thermal conductivity is important, and that's why we have been relying on the metal-based solutions. Well, the fact is that if we are choosing the right design, I can use something which is much more less thermally conductive and still achieve the performance. We have to look at additive and subtractive manufacturing approaches in order to realize those designs. When it comes to two-phase flow, which is obviously a very common phenomena which is observed in the waste heat recovery systems or heat exchangers, we definitely have to look at how we can enhance the boiling and condensation. At the bottom, you can see some techniques which have been deployed to enhance the in-tube flow boiling or condensation. And of course, that is an area where there is still a lot to be done in the context of new emerging fluids, small microchannels, as well as new manufacturing techniques. Falling, corrosion, erosions are classical problems when it comes to the waste heat recovery. If you are using an exhaust gas, then obviously you'll see a very harsh environment. So then the question becomes like how you can avoid these problems. Oftentimes people refer to the coatings which have been used extensively, but whenever we consider coatings, we have to make sure that they are durable and scalable. They're not those small scale surfaces which can be produced in clean room and cannot be realized in the actual application. And of course, surface morphology, as I noted earlier, that can lead to a higher hydrophobicity, hydrophilicity, and based on the application, we can get higher heat transfer coefficients, which can lead to improved performance. Again, the requirement is that the processes, they should be scalable and they should be durable. So shifting the gears a little bit, another important aspect when it comes to the high temperature heat pumps, and again, this is a relative term which I'm using, compressors and refrigerants are important. There has been a lot of developments, as was noted earlier by the speakers, that on the looking at different type of refrigerants and how obviously we can deploy them. Ammonia has been considered, HFOs have been considered, as Lena was talking earlier, water has been considered as a potential fluid. But I want to pose an important question over here. Is really the GWP should be the only metric when it comes to the alternate refrigerants? Um, a lot of people would say yes. Well, the fact is that we cannot really consider GWP as the only metric because, again, you have to look at the overall process. If I'm going for a very low GWP refrigerant while compromising on the COP on the efficiency, then my total carbon footprints will still be higher, right? So it has to be a good balance between the global warming potential and the resulting COP when that fluid is used in the actual application. Um, Talking about the integration opportunities in the buildings, as I noted earlier, there has been a lot of developments for looking at different residential, commercial, and light commercial applications. And this is one recent paper which shows that, well, this is a system where you can get power generation, you can get some energy for desalination, water heating is available, and you can also do the air conditioning. Seems like a perfect solution. You can get four commodities, through essentially a recovery process. You are obviously doing a lot of waste heat recovery in the overall system while deploying heat exchangers and the efficient processes. And there are tons of studies focused on the tri-generators and so-called quad generators, which can provide you multiple facilities. But one of the major questions, which has been, in my opinion, be like a major barrier to the deployment of these technologies is that they are not cost effective. So really, the major issue is how these developments can be made cost effective. Essentially, we do want to look at the combined heat and power opportunities, but they really should be meeting the specific cost measures in order to implement them at a broader scale. Elaborating a little bit more on some of the component level details, essentially waste heat recovery systems have been considered, and there has been a lot of effort on the so-called ERVs, energy recovery ventilators. Most of them, they're sensible devices, right? And if I ask you how much studies have been done on the latent energy recovery systems, then essentially there are not many. There has been some developments looking at how you can recover the moisture from an outgoing air and use that latent heat for the incoming air. But again, that has been an area which requires further development. There's a lot of opportunities when we look at the gas-fired equipment, furnaces and boilers. The exhaust gas obviously has a lot of potential. And if we have the processes to recover that, that can be a substantial benefit. Condenser heat is another area which is, again, considered as a low-grade heat. It's about 50, maybe you can get 55 degrees C under special cases. But we can use that heat if we deploy it correctly and wisely to preheat the fluid for another process. When it comes to the dehumidification, again, drying is essentially one of the major theme of this workshop. So I want to highlight about air drying processes where essentially solid desiccant, liquid desiccant, and membrane-based solutions have been considered. They are great. Again, some of the products are commercially available, but again, that's an area which requires further development to make the solutions more compact and more efficient at the same time.
Kashif, if you could maybe wrap up in about a minute.
I will, yes.
Thanks,
so
sir.
Talking about some of the low temperature opportunities, the way I think about this problem is, this is a very simple representation. There's a source, there's a transformer, and then there's an end application. So essentially, to make the overall process more efficient, we have to look at all these three components: how we are recovering, how we are transforming, and how it's being used. Things like fundamental studies are important. We really have to look at the thermodynamic analysis of each component, how it's performing, and identifying where we are losing the most exergy. Um, Techno-economic analysis is important. And we always have to consider the efficiency versus the carbon footprints, because you might have a solution which is much more efficient, but when you look at the overall context, the carbon footprints might not be acceptable. Towards the end, I will leave you guys with two major questions or areas where we should be looking at. One is, what if our source and sinks are not synchronized? And essentially, solar energy is a classical example where your sink temperatures are obviously not synchronized with the source because you are getting solar heat during a certain period of the time during the day, and you might not be using that heat simultaneously. So energy storage becomes an important area. Um, when we look at the decarbonization, we always have to look at the opportunities for the multifunctionality. And here I'm showing like a big air handling unit for, a package rooftop unit for a commercial building. It's a huge infrastructure, and I had the privileges to stand in that unit as we were developing it. It's a big structure, and it has dozens of components where obviously there are opportunities to recover the waste heat. So if we can find out the ways to use that on site, I think there's a lot of potential to make the overall process more efficient. And my last thought, when we talk about the low or high temperature, we should be mindful that these are all relative terms. And when we are defining obviously the efficiencies or the process requirements, we should consider both sink as well as our source temperatures. And that's all. Thank you.